Students, let us discuss about one of the important chapter in the vector algebra is multiple product of vectors. Multiple means many vectors. Finding the product of many vectors is known as what? Multiple product of vectors. Here we discuss about the product of three vectors, product of what? Four vectors. Namely, we come across that is three types. One is scalar triple product. Second one is vector triple product. Third one is vector product of four vectors. Meanwhile, scalar product of four vectors. Mainly we focus our attention on these only. Vector triple product, scalar triple product, vector product of four vectors, and scalar product of four vectors. As we have come across in the earlier chapters, dot product or a scalar product of two vectors. That is only for between two vectors. Meanwhile, we have come across about the vector product of two vectors or cross product of two vectors. But here, in scalar triple product, vector triple product, vector product of four vectors, scalar product of four vectors gives many applications of vectors. Namely, scalar triple product. The scalar triple product will help us in finding the coplanarity of three vectors or 4 points, or else the scalar triple product measures the volume of a parallelepiped, the volume of a tetrahedron, meanwhile volume of a prism, right? So this is the applications of what? Scalar triple product. Let us discuss about applications of all these products. Triple products or what? Vector product of four vectors or scalar product of four vectors in detail, right? Now let us discuss what is the definition of what? Scalar triple product. Now definition of scalar triple product. Scalar triple product of vectors let A bar, B bar, C bar be three non-zero vectors. You can take them as non-parallel vectors also. Non-zero vectors, then A bar dot of B bar cross C bar is a real number. Real number is known as scalar triple product. Scalar triple product of vectors. Why scalar? Of course, triple product is what? Taking the what? Product between the three vectors. Namely, it's a scalar. You can very well observe cross product of any two vectors is a vector quantity. That vector is taken dot or a scalar product with what? A bar. Therefore, A dot of B cross C is the what? Scalar. It's not a vector. So therefore, now A dot of B cross C is a scalar triple product of vectors. Instead of this, if I write, that is A dot B cross C, it's a meaningless. Or if I write that is A cross of B bar dot C bar, it's a meaningless. Why? It's a scalar. Can you take the cross product with a scalar? No. It's a vector. It's a scalar. Can you take a cross product with what? Scalar? No, it's not possible. It is not a scalar triple product. Even though the presence of three vectors does not fulfill the definition of the scalar triple product. But whenever A dot of B cross C or A dot of B cross C, next B bar cross of, that is B bar cross C bar dot A bar or C bar cross A bar dot B bar are also known as what? Scalar triple product. There is a much difference between this product and this product. Here, this is a vector. With this vector, dot is taken. This is a vector. This vector is taken dot product with what? A bar. This vector is taken dot product with a what? Vector. So therefore, this defines the scalar triple product. Ultimately, the value will be a real number. It may leads to either positive or what? Negative or what? Zero also. So therefore, it's a real number. This is the what common scalar triple product. But this will not form a what? Scalar triple product. So therefore, now all these scalar triple product are denoted by a single notation. What is that? I can write A dot of B cross C is a box of A, B, C. This can also be written as B bar cross C bar dot A bar is also what? Box of A bar, B bar, C bar. Meanwhile, C bar cross A bar dot B bar is also nothing but box of A bar, B bar, C bar. Remember, you can very well observe box of A, B, C can be written as either this, either this, either this. It means that box of ABC in the situation demand depends upon the want of the solution. We can express box of ABC is equal to A dot of B cross C or A cross B dot A C bar or C cross A dot B bar. Later we are going to prove all the three are equal. All the three are equal means this is equal to, this is equal to, all are equal to what? Box of ABC. We are going to prove that. But anyhow, the scalar triple product can be expressed in any one of the form, either this or this or this. All are equal to what? Box of ABC. We call it as aptly either scalar triple product or a box product. Box product is nevertheless what? A scalar triple product. Yes, now as I told, in scalar triple product, it has much more applications. That is, volume of a parallelepiped box of ABC can be interpreted as volume of a parallelepiped or volume of a tetrahedron. As we know, already we have come across it, as we have dealt in, that is dot or a scalar product. It's so geometrical representation as the projection of A bar on B bar or projection of B bar on A bar. Meanwhile, we have geometrically interpreted cross product. Cross product of A bar and B bar or vector product of A bar and B bar as the area of a parallelogram with the adjacent sides A bar and B bar. Then we went to find out the area of the triangle formed with the what vectors A bar and B bar as half into modulus of A cross B or half into A cross B if it is depends upon the scalar area or a vector area. Followed? So therefore, now when A bar and B bar as adjacent sides of a parallelogram, it can be interpreted as a vector area of a parallelogram with adjacent sides A bar and B bar as what? A bar cross B bar, or modulus of A bar cross B bar, as we found out many applications on dot and a vector product of two vectors. So here also in scalar triple product, geometrically we can interpret as the volume of a parallelepiped, right? Geometrical interpretation of scalar triple product. Scalar triple product. Scalar triple product. What it says, let A bar, comma B bar, comma C bar be three non-coplanar vectors. V be the volume of parallelepiped. Then the volume V is equal to plus or minus box of ABC, CC units. Why plus indicates, minus indicates? Volume cannot be negative, that everyone knows. It is always positive. But even if negative comes, we are taking into as what? Positive, by taking the modulus. So in the geometrical interpretation of scalar triple product, we are interpreting as what? Volume of the parallelepiped. Under that, we have to show that A bar, B bar, C bar are in right-handed system. Means when V is equal to box of ABC, then A bar, B bar, C bar are in what? Right-handed system. When V is equal to minus of box of ABC, we are defining it as they are in left-handed system. Left-handed system. So therefore, on the whole, so it's by leaving what? Plus or minus the volume of a parallelepiped with A bar and B bar as a coterminous edges, where A bar, B bar, C bar are the coterminous edges. Now what is coterminal edges? Like this. Okay, every such edges in three-dimensional, we call them as coterminous edges. Okay, sir, you told A bar, B bar, C bar as coterminous edges of a parallelepiped. Quite natural. A bar, B bar, C bar are non-coplanar. Being a non-coplanar, vectors are representing the edges of a parallelepiped. We have to show that V is equal to plus or minus box of ABC, or V is equal to box of ABC. What is parallelepiped? What is the difference between a cube and a parallelepiped? You take a duster, you take a what? Rectangular box. you apply some weight on a rectangular box or apply some force on a rectangular box, every faces of a rectangle will turn into a parallelogram. Such is known as parallelepiped. So therefore, when the faces of a rectangle will turn into what parallelogram, then it becomes a what parallelepiped. So therefore, now what I do is, I take like this. Join this, join this, join this. Okay. You take O, you take C, you take B, D, this is A, this is E, it's a F, it's a G. These are the vertices. You can very well observe the every faces have been turned into a what parallelogram. Therefore, it's a parallelepiped. It's a three-dimensional. Now, I take this as a what? A bar. This is what? C bar. C bar. And this is what? B bar. A bar, B bar, C bar represents the coterminous edges of a what? Parallelepiped. Now this plane, this is what? OBDC is a one plane. That plane is nothing but a parallelogram. What's the area of a parallelogram with adjacent sides B bar and C bar? Modulus of B bar cross C bar. Followed? Now it's a three-dimensional, it's a volume. Length into breadth into height we want it. Okay. Now you draw a perpendicular from A to the side OC. You call this as a M. Followed? You call this as a what? M. Right. Now if I define a what? Cross product. Define a cross product between B bar and C bar in a right-handed system. I mean, when B is rotated towards C, B cross C is the vector generated along n cap. You take OL, this is OL, you call it as what? N cap. And this is nothing but B bar cross C bar. B bar cross C bar is the vector which is generated along n cap. This whole thing we call it as OL. You know already, B cross C is the vector which is perpendicular to the plane containing B bar and C bar. Followed? Then you make a necessary construction. You call this as a N. This AM is nothing but a ON, or MA is equal to what? ON. Followed? So therefore, now I want to prove that the volume of a parallelepiped as box of ABC. Now I start. Let A bar, B bar, C bar be three non-coplanar vectors represent coterminous edges of parallelepiped. Now, what I do is, what is the volume of parallelepiped? The volume of a parallelepiped is equal to the area of a parallelogram. I can take, it's a parallelogram OBDC. It's a parallelogram OBDC into into, I call it as AM. AM represents a height. The volume of a parallelepiped is equal to the area of this face. Face is nothing but a plane, is nothing but area of a parallelogram into height AM. What is AM or MA as you please? What is area of a parallelogram OBDC with adjacent sides B bar and C bar? Is given to be modulus of B bar cross C bar into, I call it as what? ON. Right? It's also length, it's also length. So therefore, what I write is B bar cross C bar into, what is ON? Projection of A bar on B bar cross C bar. Right? What is ON? Projection. ON is nothing but a length. Length is nothing but a projection. This length is nothing but projection of A bar on ON. Projection of what? A bar on ON. Here we have to discuss about the two cases. What is two cases? As we have known here in the earlier, V is equal to plus or minus box of ABC. That explains. Plus says they are in right-handed system. Minus says they are in what? Left-handed system. So now, when the terminal point of A bar, this is A bar, when the terminal point of what? B cross C, okay, are on the same side. When this is the what? Come on, A bar, terminal point of A bar, this is a terminal point of B cross C. When they are in the same side, then A bar, B bar, C bar are in right-handed system. Followed? Then angle between them is acute, projection is positive. Followed? When the terminal points of A bar and B cross C are in opposite direction, quite opposite, in that case, they will be in what? Left-handed system. You have to change the direction of A bar. When A bar, B bar cross C bar are in what? Opposite direction, then to get into the what? Come on, right-handed system, minus A bar, B bar, C bar are in right-handed system. So therefore, now case 1 comes. What is case 1? When terminal point of A bar, B bar cross C bar are on same side, then angle between A bar, B cross C is acute, then projection of A bar on B cross C is positive, therefore, which implies V is equal to modulus of B cross C into A bar dot of B cross C by modulus of B cross C. We know that already. What is projection of A bar on B bar? On B bar, it must be there in the denominator. A bar dot B bar by modulus of B bar. In the same fashion, the projection of A bar on B cross C, A dot of B cross C by modulus of B cross C. So therefore, this and this goes. Now therefore, V is equal to what? and is we can call it as A bar dot B cross C, or else I can write box of A bar B bar C bar. This is when A bar B bar C bar are in right-handed system. That too occurs when the terminal points of A bar and B cross C are on the same side. Now when this is what A bar and this is B cross C, then the direction will be changed. Then what I do is, here it comes, case 2. When terminal points of A bar and B cross C are on opposite side, then minus A bar comma B bar comma C bar are in a right-handed system. Actually, A bar, B bar, C bar in left-handed system. You have to change the direction. So therefore, what I do is, volume V is equal to B cross C into projection of minus A bar on B bar cross C bar. Here, minus A bar, B bar, C bar in right hand system. What about A bar, B bar, C bar? They are in what? Left-handed system. That's the reason to change the what direction, we made it as what? Minus A bar. One has to understand. So therefore, I can write B bar cross C bar into minus A bar dot of B cross C whole divided by modulus of B cross this. This is not B bar cross C bar. This and this get cancels. I can write minus of A bar dot of B cross C. I can write this one as A bar B bar C bar. So therefore, hereafter, the volume of a parallelepiped formed by three non-coplanar vectors A bar, B bar, C bar representing a coterminous edges of a parallelepiped is given by V is equal to plus or minus box of ABC. Once again you see, let A bar, B bar, C bar represents the coterminous edges of a parallelepiped and they are non-coplanar. So therefore, now when they represent the edges of a parallelepiped, the volume of a parallelepiped is given by the area of a plane, this face, this plane, parallelogram, into height. Height is nothing but AM. So now I can write volume V is equal to the area of a parallelogram OBDC into AM. What is the area of a parallelogram with the adjacent sides B bar and C bar? It's given by modulus of B cross C into what? ON. This ON is nothing but AM. ON is along what? B cross C. So therefore, ON is a length. A length is nothing but a projection. So therefore, projection of A bar on B cross C. Before writing this formula, projection formula, two cases arises. One, when the terminal points of A bar and B cross C are on same side, then they will be in what? Right-handed system. Therefore, the angle between A bar and N cap, A bar and B cross C, angle between A bar and N cap is same as angle between A bar and B cross C will be acute. Therefore, the projection is what? Positive. Then I can write modulus of B cross C into, by using the definition of scalar projection, A bar dot of B cross C by modulus of B cross C. Now this and this get cancels, A dot of B cross C. Nevertheless, V is equal to box of ABC. when case 2, when the terminal points of A bar and B cross C are in opposite direction, then A bar, B bar, C bar are in left-handed system. To get them into the right-handed system, you have to change the direction of A bar. Nevertheless, minus A bar, B bar, C bar will be in right-handed system. Therefore, now volume V is equal to modulus of B bar cross C bar into projection of minus A bar on B cross C. I can write that is modulus of B bar cross C bar is equal to minus A bar dot of B cross C. So therefore, modulus of B cross C get cancels. So therefore, I can write A dot of B cross C with minus sign. So therefore, this is nothing but what? That is minus of box of ABC. So hereafter, the volume of a parallelepiped formed by the what? 3 non-coplanar vectors A bar, B bar, C bar representing a coterminous edges of a parallelepiped is given by V is equal to what? Plus or minus box of A bar, B bar, C bar. As I told, box of ABC can be written either A dot of B cross C or A cross B dot C bar or C cross A dot B bar. It means that when a box of ABC can be expressed as a 3 scalar triple product, all are equal to box of ABC. Certainly they must be equal. That's what we have to show that. What I can write is, the theory says, if A bar, B bar, C bar be 3 vectors, if A bar, B bar, C bar are vectors, then A cross B dot C bar is equal to A dot of B cross C, C cross A dot B bar. We have to show that. Now here 3 case arises. What is that is? Now, case 1. If A bar is equal to 0, or if A bar, B bar, C bar are null vectors, then A cross B is a null vector, this is also null vector, is equal to A dot of B cross C is equal to 0, this is also 0, this is also 0. Meanwhile, C cross A dot B bar is also equal to what? 0. Cross product of any 2 vectors is equal to 0. Either A bar and B bar are collinear or parallel vectors. Even null vector also. We have taken they are null vectors. Certain, this is also 0, this is also 0. This is also 0, this is also 0. On the whole, all the 3 scalar triple products are equal to what? 0. Hence, whatever the condition we are supposed to prove, it's a true. If they are not a null vectors. Now, case 2. What is case 2? If A bar, B bar, C bar are not null vectors, that is A bar is not equal to 0, B bar is not equal to what? 0, C bar is not equal to 0. Then consider, then A bar, B bar, suppose A bar, B bar, C bar can be considered as coplanar vectors. Coplanar vectors means if I take a plane, all the three vectors are lying in a what? Same plane. What's the definition of coplanarity? The vectors which are lying in a same plane or a parallel planes are known as coplanar vectors. Now, are coplanar. Then plane generated by A cross B, B cross C, C cross A is the same. That is, you call it as this is pi, plane pi. Then, why it is same? By definition, A cross B is a vector perpendicular to the plane containing A bar and B bar. B cross C is the vector perpendicular to the plane containing B bar and C bar. C cross A is the vector perpendicular to the plane containing C bar and A bar. So therefore, now the plane generated by A cross B, B cross C, C cross A is same. Is what? Same. Then plane pi contains the three vectors A bar, B bar, C bar. So now, since they are coplanar, the plane contains the three vectors A bar, B bar, C bar is same. Now, when A bar, B bar, C bar are lying in a plane, now A cross B is perpendicular to A bar and B bar. Since C bar also lies in the what? Same plane, therefore A cross B is perpendicular to what? C bar. Which implies I can write A bar cross B bar dot C bar is equal to 0. Again, B cross C is the vector perpendicular to the plane containing B bar and C bar. Since A bar, B bar, C bar are coplanar, B cross is also perpendicular to A bar, therefore dot product is equal to what? 0. Whenever any two vectors are said to be what? Perpendicular or what? Orthogonal, the dot product is equal to 0. Therefore, A cross B dot C bar is equal to 0. Similarly, I can also write B bar cross C bar dot A bar is also equal to 0. Why? B cross is also perpendicular to A bar. Meanwhile, C cross A is the vector which is perpendicular to the plane containing C bar and A bar. Since A bar, B bar, C bar are coplanar, it is quite obvious. C cross A is the vector which is also perpendicular to what? B bar. So therefore, C bar cross A bar dot B bar is equal to 0, right? This is also condition. So on the whole, we have proved A bar cross B bar dot C bar, B bar cross C bar dot A bar is equal to C bar cross A bar dot B bar is equal to 0. You say 0 doesn't matter because we have to show that all the three scalar triple products are equal. Because of the coplanarity, we have proved this equal to what? 0. When they are null vectors, we have proved they are equal. When they are non-null vectors, okay, when they are not null vectors or non-null vectors, okay, now A bar is not equal to 0, B bar is not equal to 0, now C bar is not equal to 0, then A, B, C can be taken as coplanar vectors, means they are lying in the same plane. Means the plane generated by A cross B, B cross C, C cross A is same, that is pi. You are naming it as a plane pi. So therefore, the plane pi contains the three vectors a bar, b bar, c bar is also same. Now by definition of cross product or vector product, a cross b is a vector perpendicular to a bar, b cross c is perpendicular to what? That is b cross is perpendicular to a bar, next c cross a is perpendicular to what? B bar. I have taken the dot product is equal to what? 0. When all the scalar triple product is equal to 0, hence we can say box of ABC can be written as what? A cross B dot C bar, B cross C dot A bar, C cross A dot B bar. Yes, we have come across about two cases, null vector, non-null vector, coplanar vectors. Sir, if A bar, B bar, C bar are non-coplanar vectors. Yes, just now we had one context. What is that? Geometrical interpretation of what? Scalar triple product as volume of a parallelepiped. In that volume of a parallelepiped, we have taken A bar, B bar, C bar as a non-coplanar vectors represents the coterminous edges of a parallelepiped. We have shown V is equal to A cross B dot C bar, or V is equal to A dot of B cross C, V is equal to C cross A dot B bar. Nevertheless, V is equal to plus or minus box of ABC. Now I have to show that when they are non-coplanar vectors, we have to show that volume is equal to box of ABC. Right? Okay. If case 3, if A bar, B bar, C bar are non-coplanar, then they represent coterminous edges of a parallelepiped. The volume of parallelepiped is equal to maybe A cross B dot C bar, or B cross C dot A bar, or C cross A dot B bar. All are equal to what? Box of ABC. If A bar, B bar, C bar are in right-handed system. Correct? We have proved. So therefore, now here also we have shown when they are non-coplanar, with the help of the what? Parallelepiped, with the edges, coterminous edges, A bar, B bar, C bar, we are able to prove scalar triple products are equal. They are equal to box of ABC. Sir, if now look here, now I can write volume V is equal to minus box of ABC. That's equal to minus of, is equal to minus of A bar dot of B cross C, or this may be equal to minus of B bar cross C bar dot A bar, or this may be equal to C cross A minus of C cross A dot B bar, right? Okay, if A bar, B bar, C bar are in left-handed system. Here also in both the what common cases we have shown A dot of B cross C, that is A cross B dot C bar is equal to C cross A dot B bar. All are equal to what? Box of ABC. Maybe in right-handed system, maybe in the what? Left-handed system. Yes, hereafter box of ABC can be written as A dot of B cross C, or A cross B dot C bar, or what? C cross A dot B bar. In the situation depends upon the solution, we can write as box of ABC in any one of the three types. Okay, nothing wrong in considering like the box of ABC as like this, or the box of ABC as like this, box of ABC as like this. Yes, up to now we come across about the scalar triple product can be expressed as box of ABC In turn, box of ABC can be expressed in any one of the three ways: A dot of B cross A, or B dot of C cross A, or C cross A dot B bar. We have shown under the three contexts: under the null vector, under non-null vectors, under the coplanarity, under the non-coplanarity. Next note, if A bar, B bar, C bar are three vectors and L, M, N be three real numbers, then I can write box of LA bar, MB bar, NC bar is equal to LMN into box of ABC. If any scalar is multiplied with a vector, that scalar can be taken outside from the box of ABC. How, sir? We will give the supporting proof for this. Why? We are going to prove box of ABC as a determinant of component, its component. Namely, if A bar is equal to A1I plus A2J plus A3K, B bar is equal to B1I plus B2J plus B3K, C bar is equal to C1I plus C2J plus C3K, then box of ABC can be expressed as det. First row A1, A2, A3, second row B1, B2, B3, third one C1, C2, C3. Let us see. If A bar is equal to A1I, A2J, A3K, B bar is equal to B1I, B2J, B3K, C bar is equal to C1I plus C2J plus C3K, be three vectors then box of A bar, B bar, C bar can be written as A dot of B cross C, A cross B dot C bar is equal to C cross A bar dot B bar is equal to, that is A dot of, is equal to, I can write this one as determinant A1, A2, A3, B1, B2, B3, C1, C2, C3. We have to prove that. Okay. Now the proof of this one is very simple. I can take box of ABC as namely A dot of B cross C. But B cross C is a vector. I'll find out first B bar cross C bar. This is equal to I, J, K. This is nothing but B1, B2, B3. This is C1, C2, C3, right? Now I will write I into B2, C3, B3, C2 minus J into B1, C3, B3, C1 plus K into B1, C2 minus B2, C1. Again, I into B2, C3 minus B3, C2, AD minus BC, J into B1, C3 minus B3, C1, K into B1, C2 minus B2, C1. This is nothing but B bar cross C bar. Now we want to do A bar dot of B bar cross C bar. For this vector, now B2, C3, B3, C2 minus J into B1, C3, B3, C1 plus K into B1, C2, B2, C1 dot of A1I plus A2J A3k. You know already I dot I is equal to 1, I dot j is equal to 0, I dot k is equal to 0. So by using that, take the dot product. I can write A dot of B cross C is equal to I dot I, A1I. So therefore A1 into, that is B2C3 minus B3C2. This with dot I dot j 0, this with what? I dot k 0. Next you go for A dot j, that is j dot I 0, j dot j comes minus A2 into B1C3, B3 into C1. A3k, this is what? A3 into B1C2 minus B2C1. You change as what? A, that is A dot of B cross C. I can write this one as det of A1, A2, A3. This is B1, B2, B3, C1, C2, C3. If you expand this determinant, its value is equal to this value only. Hereafter, box of A, B, C is same as A dot of B cross C is same as A cross B dot C bar is same as C cross C dot B bar can be written as determinant at the first row A1, A2, A3, B1, B2, B3, C1, C2, C3.